It better be. Yeah, it's better. Hello, everybody. Thank you for letting me know. Yeah, it's funny. I didn't even update OBS, and it just sometimes forgets. Actually, let me check the other microphone while I'm at it. Let's see here. There we go. That's a little better. I know, right? OBS, they get such a sense of humor. I'm convinced my hardware stack was reset because I was in VR and my headset just stopped tracking. I went green to red, and then none of my sensors were registering. Gave Windows a reboot. My motherboard made some weird beeps that it doesn't normally make. It makes beeps, but it doesn't usually make that sequence of beeps. And then we were back in action again. So I am very suspicious that my device IDs, which is what OBS works off of, must have gotten reset. I'm a slot the update to this program for later, though. We're definitely not doing it now. Indeed, it makes the beeps, but no boops. This is an accurate statement. I'm telling you, it has quite the sense of humor. Makes a brother sad. With that madness out of the way. Merry Christmas Eve. And Merry Christmas Day for those of you who are over the international date line. I know several of you. And if you are here, Merry Christmas. And if you don't celebrate any of those, well then, to the car commercials we go. Happy Honda Days. That's the gig. Happy holidays. All the fun stuff. It's that time of the year. Hold the door for somebody. If they're rude, hold it shut. Yeah, don't do that. Could you imagine though, like that being like, you should have held the door for me. Meh. It's like, you know what? I swear I could have remembered the expressions. I was like, you know what? I'm holding close from the inside. Good luck finding another way in. Like, yo, Porsche, look at you go. A 7 stream streak. That's amazing. Why, thank you. I suppose I am some flavor of entertaining. Thank you for hanging out. It's appreciated. What are holidays? Oh, come on, Thunder. You know what holidays are. They're the things that make you do stuff that you don't normally do, whether that may be with or against your own fruition. Oh, cool. It even gives you extra channel points for that watch streak. Cool. I don't normally see that, so cool. Cool beans. Okay. All right, we're going to do some stuff. And I said against your fruition. I didn't say against your will. Sure, they're probably one and the same, but your words, not mine. Hi, board. Welcome on in. Yeah, no, that's totally solid. Enjoy the monster hunt. We're going to be here. I'm going to give you all an update on the Protogen build because I've got some progress to share. And then I want to jump more into the Day of the Tentacle. I want to hop into that once I've expressed all of my words on Protogen things. I'm to the point right now that we've got the controllers tracking, and I've gotten the beginning framework of using ESP-NOW to send the data to the main microcontroller that will be connected to the screens. So that will give me the ability to have the controller box to be in a separate location than the screen, the microcontroller that'll be installed in the head. But I'll show you there's some tweaks that are going to have to be made to the code, and you'll see why. Because right now it's working, but it's working in a way that wouldn't be practical in a high density location like a convention. You'll see what I mean. So with that out of the way, let me get some stuff up here, and we're going to do some stuff and things. So first, I think let me take you over here just so I could show you the hardware side of what this looks like. So right now, my lights aren't on. Please hold. That's better. All right. So what we got over here is we've got two microcontrollers. I have shown you this one several times now. This is the one that has the controller itself plugged into, right? So that we have access to our top controller there, and then C and Z. Z up top, Z down bottom, right? That's plugged into this breakout board that connects via I2C or I2C. I've heard it pronounced both ways. And that's plugged into the I2Z header, right? That little guy right there on the top. And then this is the one I actually soldered on the pins. Now, ironically, I think I'm going to need the pins on the face, unless I just directly attach the microphone to one of these analog inputs. I don't know, we'll see. The beauty is that these are programmable, so I can just switch the code and plug the controller into this one and then stick this one in the head. I don't know, we'll figure it out. But this one, this is going to be the one that we're planning on installing directly in the head. Now, since I want to get the sensor data from over here, well then I needed something to connect them. Now, preferably I wanted something wireless, because if this is installed in the head, I didn't want to have to deal with this wire having to stick out of our connection port on the side of the face. Because if, say, for example, I don't want to use the controller, maybe I just want to walk around with just a head on, well then I could have it set up so that if the controller is not connected, I could just have the default face that I'll select, just like a generic, happy expression, and it would be good to go. But I didn't want it so that I would have to be plugging and unplugging the little wires, because the thing about these connectors, let me see here, I think I have an extra one, so I don't have to unconnect that one, is that they're small. These are really small, delicate wires. This is one with the actual breakout shield on it that leads to the connector head. And what I don't want to do is wear out the connector. There's nothing wrong if I were to wear out the connector on the board, because I could have replaced this. But to save myself on some generic wear and tear, I figured, well, let's keep it separate, keep it wireless, and away you go. We still have to provide power, so we're still going to have to deal with wires plugged into these. But the fact that the controller then becomes optional for the setup is what I was going for. You'll lurk for a bit. Oh yeah, totally bored. Enjoy the lurk. 2 hours, Christmas alone. Well, by all means, bored. You know where to find us in VR. So, I know I'll be on later. That is by certainly an open invitation. Okay. Yes. So that was the running theory, right? That's what got us to where we're at right now. So now what I've got is I've got code loaded up, both of these, for us to be able to pass some information back and forth. So what I'm going to do is I'm going to connect the controller to show you what that code looks like, so you can see the serial monitor, and then I'm going to disconnect this one from the computer, plug it into line power via just a regular USB-C cable that's not connected to the machine. This is just straight power. I have a power block on this bench, so that this could send signals, and then I'll plug this one in so you can see what the receiving side looks like. We're still going to look at the code of both, just so you can see how we've kind of ended up where we are. But yeah, so we're going to do that. And then I already have open on the computer the code for both, so I may have to tell it to connect to the appropriate terminal. So, all right, so we're connected there. We got green lights. Which one did it connect to? Ah, yes, it connected to the wrong terminal. That's okay. I'll fix that in a minute. Oh, we got a Xenor in chat. Hello. Okay, let's see here. So now we're gonna go over here, and this connected in the wrong order, or did it? Oh no, I'm okay. I'm okay. I I thought I opened them in the other order. If I just read the titles, I'd know. I'd know if I just read stuff. I didn't read stuff. Yeah, no, I can do that. But a moment. Yeah, bloop. I'm glad to hear that, Xenar. Much excellence. By all means, if I don't see you before the rest of today's out and tomorrow, I'm wishing you a Merry Christmas now. Whether you celebrate it or not, you are getting the cheer, okay? This is not optional. You're gonna have a good time. Oh, okay. So, to help my own brain, we're gonna reverse these because my head operates from left to right. There we go. That's the order I wanted these to be in. So you'll know that when I connected it, that the terminal is connected over here. Here, let me chill out the music a little bit here. It's getting a little angry. Nope. Nope. There we go. All right, cool. Okay, so we've got.
I'm not quite sure how to help with that.
That's a good point. All right, cool. So what we got here is we've got our code on the left side. This is the stuff for the controller, microcontroller. And then this code on our right is the code for the receiving controller. So a couple things we had to do here is we had to do our include for the controller itself. And as we had talked about previously, this is a bit of a heavy library. It takes up a lot of space, relatively speaking, compared to other libraries. It's quite hefty. So this library, if you were here for that stream, you would have seen that it crashed the Arduino I loaded it on, because it sucked up all the available RAM, and it crashed. It stopped being able to report back the data it was capturing. So we knew that though, because it said right in the documentation on Adafruit's website, this is a heavy library. If you use it, don't use it on an Arduino. You'll go boom. And when I say Arduino, I'm talking about the Arduino Uno specifically. That's what we ran it on, and it went poof. So we include the library, we make an object for it, and then from here, we then include 3 other libraries that are going to allow us to be able to interact with the ESP protocol that we're going to use to send data from the board we're on to the board we need to speak back to. Now, we have a little bit of a challenge here, and something that I don't know quite just yet is how many faces we'll be able to add to the main microcontroller, this other one, the one that's over here on the right. Because of how much storage and RAM that we're using just to send the information over. We still need room to store the faces. And if that means we have to pivot to adding a separate storage unit to house those particular files, this is going to get more complicated. I'm hoping we won't have to do that, but I'll only see that once we get to that point and we start toying around with the different bitmaps and seeing how much space we have and if the board runs stable. If the board doesn't run stable, then we'll have to pivot again, and maybe, even though this is the microcontroller that connects physically right into the displays, we might not be able to use it if I don't have enough horsepower to do both. We'll see though. We're not there yet, and I think we're gonna be okay, but if for some reason we're not, we might have to make a pivot. which and any of this stuff that's bound to happen. Okay, so something new that I added, thanks to the help of Google, is some named indexes for the different data that we're going to capture from the controller. You absolutely could have just an array with no labels and just store which element is in which position. So you could have we controller index, 0, and then element 1, element 2. Well, that doesn't tell you if that is the X axis on the joystick or if that's a button press from just looking at the code. So in an effort to make this a little bit more legible, we did this thing here where we made named indexes, and then we're going to use that when we go to load the code. I'll show you a little further down. This right here, this num of elements, is in the last element of this index, because it just gives you the number of elements by adding one extra. By adding the one extra, it counts one less, because what come on, what do arrays start with? They don't start at 1, they start at 0. So by adding that to the bottom, that actually gets us the correct count for the amount of elements in our array, because we're one less because we start at 0, because that's math. So with that out of the way, where that leads us to then is we're going to create our array object. We're going to store it in an array of bytes, right? A byte is anywhere between 0 and 255. That is 1 byte. It's a Yinks. Hi, Yinks. Ah, it's the chirpy one. Hello. I spy the cheetah. Ha. Good morning. Welcome on in. Thank you for the follow. This is an array of bytes. So we have, in this case, 7 of them. 1, 2, 6. 6. So that's 7 elements. Which, if we hover over this, the value is 7. So I don't have to count very slowly live, which is fun. And that's where that trick comes in. I love the hover. The hover is the most useful thing in the Arduino IDE. I love this. Every programming language compiler should do this. It's so nice. So this gives me a total of 7 byte values. And then we're going to use this index up here to stitch names to those. After we've done that, we then choose the channel in the Wi-Fi spectrum that we're going to send our communication on. This is something that, depending on where you live, the available channels may be different. If you live in the continental US, I believe this also includes Canada. Maybe. Shoot, maybe not. At least the US. You have channels 1 through 11. Channels 12 through 14 are in some European countries and not others. It all dictates based on your government's FCC laws. In the US, they're called the organization that is responsible for the electromagnetic spectrum is the FCC over here, but in other parts of the world, it may be called something different. I just went middle of the spectrum. The important thing that you need to do is that whatever you have on this side needs to match on this side. Because if we're on different channels, then we won't be talking to each other. They have to match. Because this is a peer-to-peer data transfer. If this microcontroller was talking to a router, and this microcontroller was talking to a router, and they weren't directly speaking with each other, then that would be okay. Because the different channels the router would be able to accommodate for, and then they could find each other via basic networking. But we're not doing that. It's a peer-to-peer connection, which means they must be on the same channel. If I speak in Dutch, you won't be able to understand me. Xenor, that is more than an accurate statement. I was crap at secondary language. I've got this one and all the programming languages I've learned over the years. Okay, I got nothing else. Okay, and loud fax tones. I got that one, but we don't use that on stream. We hurt each other's ears if we do that. That is the most important thing. I had a fantastic networking professor, and I loved him to pieces because no matter what you're doing in the space of networking, what goes in has to match what goes out. So if you're doing OSPF routing on the inside, you have to be doing OSPF routing on the outside. If you're doing BGP routing on the inside, you have to be doing BGP routing on the outside. If it doesn't match end to end, then you're gonna get garbage out the other end. Okay? The only time you want garbage in, garbage out is if you're running a trash compactor, okay? Anything else that you want to be functional has to match inside to outside. So what we're doing is we're on the same channel to have fostered communication. Now, we're going to be getting into some stuff here that was a part of the written example that was included with this class. So the code I'm working off of is available as an example. This is so confusing. It's available as an example once you have the board selected. Some boards come with built-in examples. Adafruit includes in her library example code to understand how to use some of the different functions that are a part of the board. So if I go to File, and then I go to Examples, and then we swing on down to ESP-NOW, these are the different built-in examples that we have that we could click and open, and it gives you a working example that you could work off of. And then you could toy with it and adjust it as you see fit. What if you do transition layers? Oh god, I hope not. I don't want to make it more difficult than it already is. It's already pretty bad. Okay. Now we're gonna move on to a chunk of the code I don't understand. I don't understand what this is doing in here, because I looked at like 3 different examples. This was the built-in example, and then there was another YouTube example that worked off of this example, and this is a chunk of the code they removed, but I don't know why. I also don't know what it's doing here. Oh, I figured as much. There's with the 7 layers of the OSI model. I don't want to go down to the physical. I'm already at the physical layer. I don't truly understand what we're doing here, because we call on a built-in class, and then it looks like we're making a public object of it called ESP-NOW peer, but then shortly after creating it, we call a destructor and remove it. Well, actually, we destroy the class call, but does that leave us with the ESP-NOW peer class? Like, I don't understand what this block of code is doing. I've looked at it a fair amount, and I haven't exactly been able to figure out what it's about. It's an OOP object? Xenor, could you expand on that? Because it doesn't make sense to me. Why would we stand up an object from a public class and then kill the public class's definition call? I got a little lost there. Because I can see here that we're building, it looks like the beginning of our communication here, because we set the channel and then the Wi-Fi interface. Right. The squiggly is a destructor. And I just... Yeah. Well, I figured I probably should leave it alone since I don't know what it does. And it's included in the example. I was able to follow the rest of this though. It's called when the object gets cleaned up. Oh, okay. So it doesn't get called immediately. Oh. See, this is why the chat, this is why we got the big guns here in chat today, okay? Somebody to help me understand this disaster I've gotten myself into. I appreciate that, thank you. What? You're a smart bean. I don't care what you say. You understand this better than I do. I could follow through most of this stuff, but I'm gonna tell you, sometimes it gets wild. Okay, so now what we're gonna do is we are going to start our ESP-NOW connection. Oh yeah, no, it's fine. And then what we're gonna do, so this, I am not a fan of using the reverse logic in an if statement, because this is saying if ESP-NOW.begin is not true, because there's an exclamation mark there, that we then log that we failed to initialize ESP-NOW or to broadcast appear. If that happens, we return false. Otherwise, we return true. I would much rather this be written in the other order. We get rid of the exclamation marks on these. And this is an or. So it's ESP-begin now or the add function. It's called a guard clause, but it's guard? No, that's different words. Garter clause? Wow, words are hard. And in my mind, I would just have the true be true and then the false be on the bottom. But okay, all right, guard, got it. You can follow it, but it's a little wonk. Let's see here. All right, so this is the thing that's gonna have to change, just not right now. No, I get it that it can exit early. I'm just bitching about the fact that it's written in reverse logic. Normally in an if statement, the thing that's true comes first, and then the thing that's false, or any other use case, comes second. I prefer it to just be in the default order. Yes, I could change it, but I'd rather bitch about it instead, because I didn't write it. But I kept it, and I could have changed it, but I didn't. Why? Because I don't know why. It's a good talking point. I like leaving it in there because if you do play with this example, just know that there's a reason it's written like that. The indent issue. It's fine. It's fine. All right, so this is where things are gonna have to get a little modified. Right here, you can see in the notes at the top is that this function sends a message to all devices that are within the network. That's gonna have to change. I specifically want this board to talk only to the other board that is going to accept the commands. A couple reasons for that.
Bob, can I get a glass of water?
Okay, that's fair.
Help now!
I have coffee and tea. I am prepared for this. We're locked in. Thank you for the hydrate. This is going to have to change. Functionality wise, right now, sitting in a lab environment, this works perfectly fine. Because this is going to broadcast to everybody. And then this board is currently set up to receive from everybody. When walking around a convention, when there's a bunch of different random signals that could be wandering around, the last thing I want is for either of these boards to latch on to something that's not me. That would be bad. Because if there's anybody else within ESP32 in broadcast mode, guess what's going to happen? It's going to latch on. Because right now, this is set up not to tie directly into one specific MAC address. It's tied into scan for all available MAC addresses, add them all, and then it's accepting commands from other boards. That's no good. That could cause people to cross signals. The thing that concerns me the most about this whole setup, what if it's you? If it's you, Xenor, then it's adorable, okay? Something will tell me that the screens on my head will change. If there's more than one person using this code in the same room, and they both power on their heads at the same time, the controls could get reversed, or you could have other interference. So what's going to happen to this code is that I want to bind it so that the controller that's sending is sending in unicast mode, which means I want to send a packet to one device. And then on the receiving side, only accept packets from the boards I include in this project. So for right now, it's the Wii controller, and if I can get the other one working, the RFID. So if it detects me, does it start blushing? No, it just starts scrolling good girl across both of the screens. So we don't want that to happen, or we confuse controllers. So that's going to have to change. But for right now, just working off the example code, I know that is just going to require a little bit of change up here. We're not doing that today, but I just want to mention that this is what we have, but this isn't going to be the final ads. Aww, that makes me sad. That's okay. I could fluster her again in a couple of minutes. So yeah, that's the long and short of what's gonna have to change. But for right now, all that happens is that we take the data, we take the length of the data, which is this len, and then we send it, and then as long as it actually sends, then we don't return false and we don't blow up. We then return true. It's a pretty bare bone, straight to the point kind of broadcast. Now, something specific though about a broadcast and a unicast. I could have used the circle. It's all right. We'll make some less crappy circles. All right. To reiterate myself from earlier, what does it do on the screens? It just scrolls you good girl across the screens. That's what happens. So do with that information as you will, Xenor. All right. We have broadcast and unicast. Hiya. I want to briefly mention with my really shitty circle for the broadcast, the difference between these two real quick. Because if you've got multiple peers that are available, so we have peer 1. I can't spell this morning, apparently. It would be lying then. I don't think so. Peer 2, peer 3, okay. So, and peer 4. Nope, come on. I want it. There we go. Okay. Real quick, the difference between a broadcast and a unicast. A unicast says, I want to talk. Whoops, that's not the arrow I wanted. And we'll use the pencil. That's fine. Unicast says, I want to speak directly to peer number 4. Well, it specifically calls out that peer. The other 3 are capable of seeing the unicast, but they don't do anything with it because it's a broadcast style that is specified to one recipient, not just anybody who will listen. A broadcast is the opposite of that. This one doesn't specify a specific individual. So if I want to talk to peer number 4, I'm going to send out a message, and the destination is anybody who will listen is who it will go out to. So if your board is in a sniffer mode that it will accept packets from any other neighboring board, then you'll be able to see the information because it was crafted as a broadcast. It goes to everybody. And then whoever is listening for it and can accept it in the same format is the one who receives it. One of the big things about the setup with two different boards that are talking with each other is that if I send a byte array on the sending side, well then on the receiving side, I also have to expect to accept a byte array. If I send in char format and accept in byte format, I'm going to have gibberish. I won't be able to make out what's on the other end. So just because you can capture the information, if you don't know the format it's in, well then you have to do a little bit of additional tinkering to figure it out if you don't have the code in front of you. In this case, I'm writing it, I'm working on it. And this example did not include the code here for byte values. I spent about like 4.5 hours on this, trying to kind of figure it out.
Muscle Tech Heart waits to look like arm muscles. Giggle high.
Oh God almighty. Howdy King, welcome on in. Heart wait, looks like arm muscles. It looks like muscles? What? All right, you kind of got me there. It kind of reminds me. Now that you say that, I think of the giant arms from SpongeBob when he had when we inflated his arm balloons to jerk size. That's what I'm seeing now. It's not the right color, but that's now what I'm seeing. Thank you for that. Oh, bloody hell. Yeah, we got it. So yeah, that's the thing. So that's what this does. We send the message, right? And then down here, we just do something basic. It's a global variable to keep track of how many messages that we have sent. We're not doing anything with that other than just it existing. Technology connections, wire color. I mean, yeah, I mean, that tis fair. Tis fair. After we've done that, we're then going to create the object that we're going to do the broadcast with. So we're going to create a broadcast peer object, and we just called it broadcast underscore peer. And then we have to feed into the object the channel we're going to send the message out on, which mode of Wi-Fi we're in, and in this case, we're in station mode. There's a couple different modes that are available. This just so happens to be the one we're using. And then we have a null pointer. I don't remember from the documentation what this is for. I think it might have just been required to provide some kind of pointer because of the way the code was working. The thing is that the code changes over time, so that gets a little wonky. And then this is going to be some that's familiar, some that's different. Oh, you work later on. Oh, okay, cool beans. That kind of day. So we start the serial monitor, which is what's down here, which I've actually now noticed there's nothing down here. I'll probably have to restart the board, but that's okay. We'll get there. We begin reading our nunchuck, and we set its type because this library is capable of working with other than just the nunchuck. It works with any Wii accessory from the way the library was built. So super fun. Yee! Okay, Xenor, enjoy the rest of your day. Merry Christmas to you. Enjoy all the things. I'll see you later. Okay. This is where we set our Wi-Fi mode. So this is, puts us in that station mode. There are other modes available, but this is the one we're using. And then we set our channel, and then we start the Wi-Fi session. And then from here, we're going to dump some basic information to the screen. Mary Penis? Oh, noes. All the craziness of words. Merpmis? Merpmis. Mer. I don't know. A lot of silliness at this time of the year. All right, so now we've got blah, 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 blah. Our broadcast begin. And then this is a block that will prevent us from going any further if the broadcast does not start. We can see here that if it fails, we delay for a full 5 seconds and then call upon the restart of ESP. If ESP does not start, we go no further because this if statement actually this isn't a loop, so technically this only will attempt once, and then if it doesn't, it dies, right? Because yeah, this isn't a while if loop, this is just an if statement. So basically it attempts once, and if it dies, if it dies more than twice, it just stays dead. And then we dump the version, the length information, and then we indicate setup. Now that's to initialize all of the things. Down here is where those super handy pointer values come into plan here. Now, what does matter is that the way I send the data is the way it's going to get received on the other end. So if I send the first value being value 0, right? Value 0 is the acceleration on the x-axis, and then y, z, the Joy-Cons, and then both buttons, then I just need to make sure that I keep the same pointer layout on the other side. Because if I decided on the other side to list these in the wrong order, and then maybe put the button at the top and acceleration Z down here where C is, the data is still in this order. It's being sent in this order. So I need to make sure I store it in the same way that I sent it. Otherwise, I'm going to have some very, very strange results. And then all we do is we take our numchuck object, and then we just get the values, just like we had done before previously. I commented it out just to include it down here. This is the code we had used in a previous example to just show us the, the basic functionality of said controller. And then we have print a blank line. And then down here is where we're going to do the broadcast. So down here we see we have broadcasting peer, we're sending the message. And then this is pretty straightforward. We send the entire array of byte objects. We called it controller data. And up here, all we did is just set each individual item that's in said array. Now, the ESP-NOW is capped at, or recommended to go no more than 250 bytes per transmission. We're transmitting 7 bytes. Bytes 0 through 6. So that's well underneath the bandwidth capabilities of ESP32 now. And then we just list the size of the data. And the reason we send the data in the length of the data is so that the receiving end knows how much data it's about to receive, and then the actual stuff. And then after that, we just print, assuming that it didn't fail, which is what the exclamation mark is again. We were quote unquote successful, and then we're just delaying for a full second, just to make the code seem, readable. In practice, this value will get reduced. It'll probably be something around the lines of like 200 milliseconds, just a very small delay so that we're not completely blasting the airwaves. But again, once it's switched over to unicast mode, sending out to just one specific board, it's still putting the radio waves out into the environment, which is why they're separate channels. If one channel is particularly noisy, then you may need to switch channels to be able to use your stuff. In one of my networking labs that we did quite some time ago, we had taken a bunch of wireless USB sticks, wireless adapters, popped it into USB, and then everybody in the lab was instructed to be on channel 1. This was a room of like 30 people. And then we were told to try to transmit to our neighbor. We were all given an address, and with all of us on the same channel, we were all screaming on the same channel. Well, let me rephrase a little. Our device was supposed to connect to the router, and then from there, or from wireless AP in the room, through the router, through our neighbor, with the address we were given. And with all of us on exactly the same channel, we couldn't transmit and we couldn't receive because there was too much noise on the same channel. So by us all jumping up between multiple channels and a couple people overlapping, because there was more than 11 people in the room, because in the US it's channels 1 through 11, we were able to transmit and receive without any problem. So right now, even though I'm hard coding a channel into this, I'm kind of curious to see how that's going to behave in the real world. I'm kind of hoping that since the devices are going to be pretty close to each other, that we won't have too much trouble with interference. But if it does end up becoming a problem, might have to revisit that and make the code a little bit more robust to be able to figure out its own channel. But the trouble is that we have two boards that need to be able to talk with each other. So we would need both boards to come to a common consensus and still be able to locate each other. So for right now, we're not looking to make the code more difficult than it needs to be. And right now I think we'll be okay. But if it turns into something that it's problematic, then we deal with it then. Something to keep in mind. Another way to think of the channel you're on is being in a room full of people. Go to a karaoke bar, right? Picture everybody who's in that room being on the same channel. There's the bartender talking, there's the glasses clinking, there's the people at the tables, there's the people screaming up on the main counter with their karaoke mic, and they're shrieking and doing all the things, and they're a little wobbly because it's a bar. That's very hard to get a clear message across. And you're probably going to have to get pretty close to the next person to be able to even get your point across to them. Now picture that same bar was broken up into multiple rooms, right? You got the room in the back where the bar is. You got a room off to the left where the karaoke is. You have the front entrance area where there's just tables and maybe it's a bit of a quiet restaurant. It's sectioned across multiple channels, multiple containers, so that people can hear each other. Same thing happens in technology with the electromagnetic spectrum. That's part of the reason why the FCC exists in the United States, is to dictate at a governmental level who has access to which chunks of the electromagnetic spectrum. Because ham radio gets a chunk, satellite gets a chunk, Wi-Fi that you use in your house that is unlicensed gets a chunk. You do not pay the FCC to use the equipment in your own home. It's considered an unlicensed band. You don't have to pay anybody to use that. It's just something that you use, which is what this equipment falls underneath. It's unlicensed. It doesn't require to pay anybody to use it. There are certain aspects, certain wavelengths and frequencies that you do need to get a license for. Ham radio is one of them. In the US, you need a ham radio license. You could buy the equipment, you could turn it on, and the equipment will still work without the license, but to be legally using that license, or using that frequency, you need a license. And that just helps with not overlapping with everybody else, because we only have a finite amount of spectrum we have to share. And as technology has changed over the years, that's something that frequencies have been taken away and then given back. The frequency that was used for 2G and 3G cellular service in the US had been repurposed. It had been taken away from the cellular perspective, and I want to say that was given to the ham radio people, if I remember correctly. It was reused. The point is that it's no longer used for cellular, directly speaking. So that's that little bit of communication station. So now let me reset the board, and we can at least see what's in this terminal. And then we'll connect the other one, and we'll see what that looks like. Reset. Oh. Okay, so I don't have any print statements in this code anymore. So we will see nothing in this terminal that's down here because there's nothing to write to the terminal. But that's okay. It's working. And you'll see that it's working when I plug the other board in and when we start receiving data. So what I'm going to do is I'm going to disconnect our board here. I'm going to move it to the other dedicated power source I have in this room. So this one's going to get disconnected. And then this is the one that's going to receive information. So that's going to get plugged in. And then this, I'm going to move over to one of these other USBs. Then I have this just here, just to supply power. All right, so we're lit up over here. Green light, green light. And then we're going to plug in our receiving end. Now, since the receiving end is set to receive from anyone, then this is going to immediately start showing data in the terminal. So I've got that connected. Okay. Now, on the receiving side, we have over here our coordinate information. Now, I'm gonna let that just cook right now while we're gonna gloss through the code for the other side. Now, we're gonna do a lot of the same stuff here, including a lot of the same libraries, right? And then we're gonna end up having this extra one for vector. And why did we include that? I vaguely remember what that was doing in here. It was one of the computations down here it was needed for. Shoot, I don't remember. Well, that's okay. Point is that it is required for one of the operations that happens further down in the code here. And then same as before, same channel, we're on 6. And then as Xenor had lovingly explained for the toaster that didn't understand, this was for the class call and then the destructor when it was needed. Now, this right here, function to register the master peer. This is the section that I mentioned that also needs to change on the other side of the fence. This is set to accept anybody who is broadcasting out on a whim. So right now, this will accept anybody. And then start receiving information. Now, if the other side of the fence was transmitting data in a different fashion or a different payload, and the code on this side wasn't prepared for that, where we would just see gibberish in the terminal behind my head. Now, that index that I used before is exactly the same index here. It's exactly, I literally copied and pasted this block of code to bring it over here. And then it's the same order. Super important that it's the same order, because this is the way that it's going to be received. The biggest trouble I had with trying to write this was trying to understand, well, okay, I sent over 7 bytes worth of information. How do I get it back out? Because it's shot across the airwaves, and as the code goes right now, it doesn't really know. It knows that I sent a byte, and it knows the length of the byte. But beyond that, how do we deal with the information, right? So, same thing with the initialization. We make another byte array using the number of elements, 7 elements, 0 through 6, right? I called it the same exact thing. This was not required to do, because the data on the other end doesn't care what it was called for on the other side. All that matters is that you understand your code, and in this case, it's sensor data from the controller. Why change the name? This makes it easier to read. So I kept it the same. And then down here, we have a void function. This is outside of the main loop. I want to make sure that that's very clear. The main loop is all the way down here. All the way down here. This is the main loop of the code. All the way down there. But the function that actually receives information is all the way up here. And this is called onReceive. Now, what we do is we spit out the MAC address of the master, and then if it was a broadcast or a unicast. Right now this code is working in broadcast mode, so we're spitting out the word broadcast. Now, this next part, I had a lot of trouble trying to load these elements via a loop, with the fact that I named them using the indexing names that I used further up. So instead of having a loop to load all 7 elements, 0 through 6, I just manually tore apart the payload that came across and then just stuck them in here across 7 lines. So the acceleration data for the x-axis was sent over in data position 0 in the array, and then it was y, z, and so on and so forth to get the rest of these. Something to note about the buttons for buttons C and Z is that in our example code, I don't know if I touched on this, I don't recall. If the button was pressed, that would make it true, and we'd see it print the character to the terminal. The buttons themselves are either true or false. They are not their letter. So to make it easier for us to visually see which button we've clicked, we then just dump to the terminal that we've clicked the C or that we've clicked the Z. We absolutely could have it just dump true and false. The board disconnected. That happens sometimes. I don't quite know why. It could be the speed. I'm not entirely sure, but ignore that. That's probably going to happen a couple more times. So yeah, we accept it in the function, and then we just dump it to the terminal so that we can see what came out on the other end. So this is the same code that we used before, and the only thing I changed...
Bob, can I get a glass of water?
Don't mind if I do. My coffee's getting a little cold, so I should probably finish it. Also, welcome on in, Dredron. Happy holidays to you. Yeah, just to see what's in here, we just dumped it to the terminal so we could see it. Proof of concept that it's working, really, more than anything. Yeah, absolutely. Oh, that's where that vector comes in. So list all the masters. It will populate when a new master is registered. Note the pointers. Note, using pointers instead of objects to prevent dangling pointers when the vector reallocates. So we called vector because we're working with pointers, not objects. I'm gonna be real with you. That arrangement of words is above my pay grade. So I would not be able to express it other than the fact that pointers, I know pointers are smaller than objects. But this part here, pointers instead of objects to prevent dangling pointers when the vector reallocates. It looks like it's a memory saving thing that it's doing by using pointers over creating an object. I'm not entirely sure on the theory behind it, but all I know is that it was noted there. Do it this way. And I went, okay. I'm not going to argue with the sample code unless it doesn't work or it runs poorly. And then a block of code that exists right now that will be going away is the register new master. This is how the board is blindly accepting transmissions from a MAC address it does not know. It takes a look, and the only thing it cares about is that we're on channel 6. It's hard-coded to be anything that's on 6. If it's broadcasting on another channel, it is ignored. And then it has an ad here. And the ad captures the MAC address of the peer, the Wi-Fi channel it's on. It then stores it that it's in station mode and then hands it a null pointer. And if it fails to add it, it deletes it. And then we just basically have some messages here and some logging functions. This is also a little bit of additional code that we don't necessarily need, but it's, you know, useful information. And then down here, it's gonna look a lot the same. We're gonna put ourselves in station mode. We're gonna start the Wi-Fi module. And then we're just gonna dump some basic information to the screen indicating that we are operating in slave mode, broadcast slave, which means we accept the data from everybody who's on the same channel. That's dumping out anything that's in broadcast mode. And then we dump our MAC address to the screen and which channel we're playing with. We then initialize ESP-NOW. We delay 5 seconds at restart if it fails. That only runs once if it needs to. Usually doesn't. And then let's see here. This is dumping some basic information about what flavor of ESP we're on. And then this calls the onNewPeer. So this onNewPeer is the call to the function. We look that up here. onNewPeer, I think I scrolled past it. I did scroll past it. Let's see here. I will find you. One of one. Interesting. Oh, that's a call of this. Oh, okay, that's a call of the library. Never mind. That's not a function we declared. That's a function. That's a function that's built into the library. So by doing the period and then the name of this, we're going into the ESP-NOW library and then calling on what to do if there's a new peer present. And then we call on register new master, and that we declared up here. That's this void, which a void function is a function that does a bunch of stuff, but doesn't return anything directly back to the program. It does things, but it doesn't hand anything back. It just does what it's supposed to, which it still can manipulate things. Like in this case, it's registering that MAC address and storing it into the program. And then it's available further down and it could go ham. And we could do transmissions and receives. Where am I at here? Yeah, so then once our setup is complete, we then hit the loop here. And it says print debugging information every 10 seconds. Which, if the millisecond is less than last debug, which is greater than 10,000, register masters. Right. Now, something that's particularly weird about this code is that you'll notice that there's nothing in the loop that calls on the data receive. So up here we have a function that's called onReceive. And if I go looking for that, it's not called at any point, which seems awfully strange. And the reason I believe that's the case is because data... Oh, I thought that got blocked by AutoMod. Hi, Pyrex. Pyrex, you turned this really weird shade of red in my other window here. And I'm like, why? Why would AutoMod do that? It's like, you're trying to be festive. No, you're not. Like, oh, that's so rude. Merry Christmas to you as well. The reason I believe that this is working, even though we don't call it in the main program, I mean, it might be, but the highlightation is very strange on Twitch. I tell you that right now. The reason I believe that it just works, on receive is a part of ESP-NOW. So I believe what's happening is that the function is called on receive, and that's an interrupt, which means that whenever there's data, it then just runs the on receive. You could be anywhere else in the program and it still runs this block of code. I believe that's because of the name of this. I do need to look a little further into that. I do need to get some clarification as to why that works, but I believe that's what's happening. I believe it's because it's an interrupt. Because if you're transmitting data and you're mid-loop doing something, well, then you're going to miss the data, or you're going to have to ask for it again. So by being able to pause the code for a brief moment, accept the stuff, and then go back to what you're doing, allows us to get into action. Now, as you've seen, the messages that have been scrolling behind my head here, let me move this so we're a little bit more centered here. Oh, come on. Come on. I want to readjust the window. Alright. That's better. Okay. So I am going to take a second and I'm going to reset this. I'm going to unplug the receiving board. I'm going to clear the terminal, and I'm going to start it back up again. Now, you'll see that it's got information here, but at the top of the code in that setup section, there's a section of print statements that are supposed to print during first time setup, which includes the ESP revision, the board information, the MAC address of the master, all of those things that we said that we wanted to briefly appear on the screen just once at the beginning of the program did not present themselves. I don't entirely know why sometimes those print statements in the initial setup sometimes show up, sometimes they don't. That's something I would love to get a little clarification on myself, because I don't quite understand what makes that happen there. But nor here nor there. Now that we have this up, I'm going to grab the controller and I'm going to start clicking buttons. So I got the controller in my hand, and just moving it around, you're going to see that the X, Y, and Z values, they're on the top here, are going to change as I'm just moving the controller around. I'm not clicking anything. Now I'm going to hold the C and Z button. And you can see those registering. I'm going to let go of Z. Switch. Engage both. And let go of both. So there's proof that the buttons are registering wirelessly. Now I'm going to move the joystick around. So I'm going to go to the bottom left-hand corner, and that's going to get me the joy values of 0, 0. And then I'm going to go to the upper right-hand corner, which is going to get me 255 over 255. And then I'll just cycle through a couple of these other positions and spin through them. So what we're going to do to change the faces is we're going to use the coordinates of X and Y on the Joy-Con to be able to tell the main microcontroller, which will be this one, the one for screens, to switch through the different expressions. And it's just going to be based on a little bit of math. We're not going to have to really compile any math. We're just going to simply say that if it matches these two coordinates, switch to this bitmap. And then it'll be that. I know it's math, but the reality is, at least it's not hard math. We're just passing numbers that are stuck on a map. So yeah, that's long of short where we're at right now. Now, to prove that this is very wireless, I'm going to disconnect the transceiver for a moment. So the Wii controller board is going to get unplugged, which is going to stop the data from flowing. I'm going to reset the terminal. And then I'm going to take myself into another room, plug this back in, and move the controller around. And you're going to see... Interesting. How is it registering about... I mean, in fairness, it's in broadcast mode, so God knows what it could be registering. Interesting. Is it registering itself? Nope. That's somebody else. Well, that's fun. That's the other reason why we need to get this off of broadcast mode. I want to only talk to the one I want. So I might actually have to come back in here and reset this code, but proof that this thing is wireless. We are going to take this one into another room and then leave this guy here and get some proof that this will work. Now, supposedly this will work at a distance of up to 700 feet open air, which is crazy. All right, so now we've got sensor data flowing through again. And just like that, from a room over, I sent coordinate information. I just realized I never switched scenes. Let me do that again. I just moved and sent sensor information, and that was on the wrong. Yay! Let's try that again. Indeed, the wibbling and the wobbling. Kind of neat, right? And the other thing too that I really love about the fact that we can accept information at a distance is that if you have a handler that's working with you and you want both of your hands available to be the brute, the handler could have the controller for the expressions and do the emotes on your face on your behalf, while you being able to hold that center of attention with those that are in front of you. Whether you're, doing photos with somebody or you're doing meet and greets, that kind of thing. This gives you that little bit of flexibility that if you want somebody else to be able to control your face, you can. Because you could be not physically connected. That's the other reason that I wanted to do it this way. So I have a little bit of tweaking I needed to do to get it out of broadcast mode into unicast mode, but I have another example to play with that I think is going to be pretty damn amazing. So I'm hoping that before next time I can figure that out. I am very much keeping track of and backing up this code as I go along. So I already have an offline copy of the broadcast setup in case I thoroughly screw up the code. I could fall back onto it so that we don't lose this, because it's terrible to lose code that was working. So I'm pretty in the know about keeping revisions of my stuff. So I don't screw myself. So yeah, that is the code portion of today. So now what we're going to do is we're going to pivot into our game. Just give me a moment here while I get us sorted up here.